All right, in this worked example, we're taking a look at a preview of things to come and a review of vector addition. Question number 1A reads, the Young modulus of a metal of a wire is 1.8 by 10 to the 11 Pascals. The wire is extended and the strain produced is 8.2 by 10 to the negative 4. Calculate the stress in gigapascals. A key strategy to being successful in physics is memorizing as many equations as you can, okay? So Young modulus is a way to sort of measure the strength of a material. We use the letter E for Young modulus. Sorry about the autofocus there. We'll try to, if it's ever blurry for a bit, and you're like, wait a minute, we'll let our eyes adjust, okay? And they give you the Young modulus. Note that it's in Pascals. Those are the same units as pressure. Strain doesn't have any units. Young modulus E is defined as stress over strain. So Young modulus is stress over strain. We use the Greek letter sigma, lowercase sigma, for stress. We use the Greek letter epsilon for strain. So in variable form, I'm going to have to write out the word stress and strain. We know that those letters stand for that. Stress is defined as force per area, the same way that pressure is defined, and this is why we get units of pressure for Young modulus. Strain is defined as the extension of an object over its original length. So for this example, we have a metal wire. You may recall from chemistry that metal is ductile and malleable, so it can be drawn into wires. They're malleable. They can be, sort of manipulated without breaking. And so the strain tells us if we were to stretch out a wire by 1 centimeter, but the original wire was 1 meter, 100 centimeters, then the strain would be 1%, right? 1 centimeter out of 100 centimeters. So you can report strains as a percent, like I just did, or as a decimal, like they've got here. But note that because both of these are lengths, the units are canceling out. So there's no units with strain, okay? 8.2 by 10 to the negative 4, no units because it's just a ratio of lengths, extension to original length. So because we're solving for stress, they give us the Young modulus and the strain. We just have to sort of rewrite this to make stress the subject, is my suggestion to you for how to deal with this. And so the stress then is going to be equal to Young modulus times strain, right? Just multiplying both sides by strain. Now I could substitute in values. The Young modulus was 1.8 by 10 to the 11 Pascals. The strain was 8.2 by 10 to the negative 4. Calculator, 1.8 times 10 to the 11 times 8.2 by 10 to the negative 4. Get that number.
Wait, what represents stress?
Stress is this Greek letter sigma, lowercase sigma. Stress equals Young modulus times strain. Because Young modulus is stress over strain, I've just multiplied both sides of this equation by strain. So stress equals this times this. All right, that's it. 147600000 is the answer I get. 147,600,000. And then the units here are Pascals, right? Because there's no units here, so I multiply Pascals by nothing, I get Pascals. Now I need Gigapascals. Yes. I would suggest if you don't already have a calculator out to get one out and to look at the number there in your own calculator, like practice doing the calculation for yourself and build your confidence that, yep, I'm seeing the same number in my calculator that you're seeing in yours. If I were to, and I'm not saying I'm going to, but if I were to do a calculator check today, would you earn the 50 points?
Yes.
You would. Would you tomorrow? That's when it really matters, okay? And I hate to give a student a 0 out of 50 on a calculator check on quiz day because they're probably not going to do so well in the quiz either. You need your calculator. But I got to keep you honest, and so bring those calculators tomorrow. Quiz day, it's really important. Any other day, it's like, fine, just use any calculator, but on the quiz, you have to use a scientific calculator. You can't use your phone. So it's better than doing nothing to just calculate in your phone, but even better yet is getting a calculator you're allowed to use on the quiz. And so that's the number that is the product of these two terms. To convert Pascals to gigapascals, set up a conversion like this. Put the unit that you don't want to be in the denominator, so it's going to cancel. And then you have to know, what is a gigapascal? Giga means billion. So there is a billion, 10 to the 9 pascals in 1 gigapascal. This is just a conversion to go from gigapascals to pascals. Giga means billion. It's like 1 billion pascals, 1 billion pascals, same thing. What this suggests is that I got to divide by a billion, right? Take this number in pascals divided by a billion, and I'll cancel out pascals, and I'll be in gigapascals. Dividing by a billion is the same thing as moving a decimal point over all 9 places here. Or you could have the number in your calculator and say divided by 10 to the 9. So divide by a billion equals. And it's the same answer as moving the decimal point over 9 places. So you get an answer of 0.15. Good. 0.15 is the best answer. And the reason why I wouldn't write 0.1476 is because that's 4 significant digits, and I've only got 2 significant digits here and here. So I kind of want to let the precision of the values that went into the calculation guide the precision that I report my final answer to. Let your eyes adjust. There they go. All right, the next one says, an electromagnetic wave has a frequency of 12 terahertz. Calculate the wavelength in micrometers. An electromagnetic wave is light. All light travels at a constant speed, so we use letter C for that. Note for this problem, you needed to know that key equation. Without it, you would have been at a loss. Without knowing that giga means 10 to the 9, there's no way to get to that correct answer. So you got to know your equations. You got to know your metric prefixes. The equation for the speed of light is that it's equal to wavelength. We use the Greek letter lambda for wavelength. Kind of looks like that symbol. And the speed of light is equal to wavelength times frequency. The speed of light is 299,792,458 meters per second. But you don't need to remember that. You can round it to 300 million. So in fact, that's the value you should use when you calculate with the speed of light. Even though we know it very precisely, we tend to just calculate with this rounded value. So just calculate with that one. That's just so, for your own knowledge. Just like I did up here, I made sigma the subject. I really should make wavelength the subject, right? And so let me rewrite this equation like lambda equals speed of light divided by frequency. Right? Dividing each side by frequency, you can get that. So I've got the speed of light divided by the frequency to give me my lambda over here. And the frequency is right here, given. 12 tera, and then hertz are the same thing as reciprocal seconds. A hertz of frequency is like how many waves per second. So the units are really per seconds. Hertz is the same thing as reciprocal seconds or per seconds. And so these per seconds cancel. I'm in meters when I do this calculation. You must use grouping symbols when you divide by a value in scientific notation. Type it in your calculator like that, not the way it's written. You will get a very incorrect answer if you just type it in the way that it was written before. So if I just go 3, 5, 10 to the 8, and I get that, 300 million. And if I just sort of push the buttons like this, divided by 12 times 10 to the 12 equals, I get a number that's very wrong. 2.5 by 10 to the 19, it's like the 2.5 is good, but the order of magnitude is off by a lot, like 24 orders of magnitude. Like, All right, I'll send them. Jason at 11:40 for being checked out. Up to you to remember that. So that's not the correct answer because I didn't give my calculator the language it understands. My calculator divided by 12 and then it multiplied by 1,000,000,000,000 because that's the order of operations, right? It knows to multiply and divide from left to right, the order that it's written. But it also knows to do parentheses first. So I took a number and I divided it by 12 and then I multiplied it by 1,000,000,000,000 and I got a huge number because I multiplied it by 1,000,000,000,000. What I really wanted to do, if I can sort of get a clear sort of thought on this, some clarity here. I can think clearly, clear thinking, autofocus, come on. Camera. There, now I can think clearly. Then I'm dividing by 12 trillion. I'm dividing by a huge number, right? Like this number is bigger than that number. Even though 300 million seems like a really big number, 12 trillion is even bigger. So if I type this in correctly, 3 by 10 to the 8th is that number, divided by, use your grouping symbols, open parentheses, 12 times 10 to the 12th. When I close parentheses, yep, that's this number, right? You see how this isn't technically correct scientific notation? Like we want the decimal after that 1, but your calculator doesn't care. Get in the habit in physics of knowing that tera means this order of magnitude. And you can simply convert things by going 12 tera. So 12 terahertz. And your calculator will deal with the scientific notation for you. Like 12 by 10 to the 12 is the same thing as 1.2 by 10 to the 13. You just sort of take an order of magnitude and put it over there from here. When I hit equals, it should give me the correct answer, right? Because I already hit divided by, open parentheses. When I close parentheses, it shows me the thing I'm dividing by. Good, I like seeing that in my calculator very clearly. Equals, that's the correct answer. So see how the 2.5 was good, like it knew how to get the odd sort of coefficient in front correctly, but because you were multiplying by 1,000,000,000 instead of dividing by 12 trillion, you got an answer that was like way too big. And you should look at the answer and go, wait, a wavelength of like 10 to the 19, that's like almost as big as our galaxy, our solar system. Yeah, that's a lot of meters, okay? But this is more reasonable. So we get a wavelength of 2.5 by 10 to the negative 5 meters. Okay, now we're in meters, but we want to be in micrometers. So the same way that we converted our final answer up here from Pascals to gigapascals, we're going to cancel out meters. We're going to go to micrometers, this Greek letter mu, it's micro, like a U with a line on the side of it. And there are 1,000,000 micrometers in 1 meter. Micro means 1,000,000th. So a micrometer is a millionth of a meter. If you took a meter stick, like you were using yesterday, and you divided that stick into 1,000,000 equal sections, each section would be 1 micrometer long. Mathematically here, we're just multiplying this by 1,000,000. Our meters cancel, we're in micrometers, so times 1,000,000 equals 25 micrometers. You are expected, by the time we study chapter 13, I think, to state the wavelengths of the principal radiations of the EM spectrum. The principal radiations are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, and you got to memorize like how big of a wavelength goes with each one of those. I'm pretty sure this is infrared. I think that's infrared, but I have to think through it a little bit more. All right, on to the review question. So that was a preview of some physics that's, we've really yet to study, but you want to sort of take away from this at this point in the year. 1, it's important to memorize equations. 2, you got to know your metric prefixes. Okay. All right, so now we've got a situation where an object B is on a horizontal surface. 2 forces act on B in this horizontal plane. A vector diagram for these forces is shown to scale in figure 1.1. That's kind of nice, it's to scale. What are we going to do with this? A couple of things. They tell us sort of that information again. They also give us the mass of the object in grams. It says on the figure, draw an arrow to show the approximate direction of the resultant of these 2 forces. So that's adding vectors, right? That's what's on the chalkboard. That's what we've been practicing. adding vectors. It asks us to show that the magnitude of that resultant, of that vector sum, is 6.6. So they tell us the answer, prove it, show us that it's that. The question goes on to read, calculate the magnitude of the acceleration of B produced by this resultant force. We're going to take care of this one right now together. F equals ma. Even if you didn't know how to show that the resultant force is 6.6, you at least know that the resultant force is 6.6. So we know the resultant force. It's 6.6 newtons. Remember from week 1 what a newton is. A newton is a derived unit that's equal to a kilogram meter per second squared. We're going to solve for acceleration in meters per second squared. And in order to do that, we're going to have to substitute in the mass of this object, not in grams, but in kilograms. So yet another sort of metric conversion that we've got to do here. And by the end of the year, or maybe even before then, you should feel comfortable enough just going, okay, 750 grams, that's 0.75 kilograms. And if you like to get in that habit of very formally setting up these conversions, then you realize that there's 10 to the 3 or 1,000 grams in a kilogram. Kilo means 1,000. So we're taking this and dividing it by 1,000, moving the decimal point over 3 places. So a kilogram meter per second squared, that's what a newton is. Because they tell us the force in newtons, we're restricted to those units of mass by definition. So that's why base units are really important. You know, you get the wrong answer if you plug in 750. Got to plug in 0.75. Now we can solve for acceleration, dividing each side by 0.75 kilos. And you should get 8.8 when you do that. Your calculator takes 6.6 divided by 0.75. And a newton per kilogram is the same thing as a meter per second squared. That's actually up there on the chalkboard for the astronomy course we get. The last step is to determine the angle between the direction of acceleration and the direction of the north force, which was 7.5 newtons. So these are vectors. The direction of acceleration is conveniently in the same direction as the resultant force. So when we do this question, we draw an arrow showing the resultant. That's the same vector that we're accelerating in. So let's go back to that. Let's take a look at this and say, okay, I'm adding some vectors here. I got 2 vectors that are acting on object B. But I need to know how to add vectors, and I don't know. So I look up at the chalkboard and I see step 1, place vectors head to tail. Sometimes that's done for us. Is that the case here? Are these vectors head to tail? They are not. They're head to head. Okay, if you look at them, the head of this vector is here, the head of this vector is here. They're pointed head to head right now. So I've got to move them around. I've got to put them so they're head to tail. That's the first step in adding vectors. So rather than having the tail of this vector up here, I want to put the tail of it right here so that it's at the head of this first vector. So this one plus this one, the tail is there, so it kind of goes like that. So that vector, I'm moving it right there. It's still the same vector, right? It's still 2.5 newtons. It's still pointing, you know, this direction. It's like 30 degrees above horizontal. Down and to the left, southwest, okay? Step 2 on the chalkboard says connect the tail of the first vector to the head of the last vector. That's your resultant. Okay, so that's the answer to part 1. If you're pushing something this way and that way, which way is it going to actually move? It moves like this. Okay. The down component of this force steals away from the 7.5 newtons north a little bit. Like this brings it south a little bit. The west component of this force is the one that brought it over a little bit. That's why it moves sort of northwest. What I need to do to show that the magnitude of this is 6.6 now, right? They tell me that this should be 6.6. Could use a scale drawing, right? It is to scale. So like if I set a scale like that long is 2.5, that long is 7.5, I could measure that. You'd probably need a protractor too to like get that angle right. You can use a scale drawing. We're going to use resolution of forces because step 3 up there says resolve vectors into perpendicular or x and y components. So let's do that. This vector is already in its x and y components. It's just a y component, right? 7.5 north, newtons north. This one is not perfectly aligned with north, south, east, and west though. It's going southwest. So how much of it is going south? How much of it is going west? That's what we got to do to resolve this vector. Now, even though I already moved the vector here to see my sum, I'm going to kind of do my working over here on it since it's already kind of nice and, you know, kind of labeled there for me. I'm figuring out how much of this down to the left vector goes down, how much of it goes left. I'm just going to figure it out over here. So this down component, I'm going to call it the force in the y direction. This left or west component, I'm going to call it the force in the x direction. This is my force of 2.5 newtons, a hypotenuse. Now we're going to use some trig. Start with the y component. Everybody should be able to look at this and go, it's opposite this 30-degree angle. That component there, once we can think about it clearly, there we go. We can see that it's opposite the 30-degree angle. We know the hypotenuse is 2.5. The function that relates opposite and hypotenuse is sine. So, TOA, if you need to remember that. So I can solve for this by saying, okay, the sine is helpful here. The sine of 30 degrees, the function of the angle, equals this ratio of sides. The opposite, the force in the y direction, over the hypotenuse, 2.5 newtons. Perfectly solvable math problem. Okay. Multiplying both sides by 2.5 newtons, I realize that the force in the y direction is 2.5 newtons times the sine of 30 degrees. Some students may have studied, you know, enough pre-calculus or whatever to know that sine 30 is a half. Or if you didn't know that, just type it in your calculator. You get a calculator, right? Use it to your advantage. 30 sine 0.5. Half of 2.5 is 1.25 newtons. That's my component down for this vector. A vector that goes 2.5 newtons this way is 1.25 newtons down. How many left? Two ways to solve it now. I could use Pythagoras theorem, right? Like I've got a right triangle. I know the hypotenuse in one side, so I could do a squared plus b squared equals c squared and solve it for that. Or I could use the cosine function, right? Because the cosine relates the adjacent, so that side is adjacent to this angle, and the hypotenuse. So I'll use the trig here. The cosine of 30 degrees equals the side adjacent, the horizontal component or the x component of my force, and my force was still 2.5 newtons. So I only have to resolve this vector because this one is already kind of resolved for me, right? So it's only going vertical. The same way I solved this one, I could solve for the x component of force as 2.5 newtons times the cosine of 30 degrees. The cosine of 30 degrees is 0.866 times 2.5, and I realize that the left or the west component of my 2.5 Newton force is 2.16. 2.17, I think is actually better rounding. 2.17, that would round. Okay. Here's my result. 6.6 newtons. I know I have to show that it's that. My resultant is itself composed of components. It has a left component and it has an up component. Who out there knows what the up component of that force is? Lucas. It's not 7.5 minus 2.5 because that's not vertical, right? The 2.5 goes this way, but it's 7.5 minus 1.25, right? Like, look at step 4 up there. It says add the horizontal components together. I'll do that one for you. You're welcome. Oh, 7. Because there was only one horizontal component, right? It came from this one. I didn't have anything to add it to. But if you look at step 4B or whatever, add the vertical components together. So 7.5, what's the vertical component of that force? That's 1.25. So it's the one that brought it down a little bit. See how this resultant isn't as big as the 7.5 this way, right? It brought it down by this much. And so the net component in the y direction for my resultant has to be 7.5 minus 1.25 or 6.25 newtons, right? The 6.6 was my hypotenuse here. So I know that the up is 6.25, right? It's the sum of my vertical components. This one's down, so I got to subtract it from this, right? They oppose each other. My left is 2.17. I'm going to rewrite all of this right here, where it says to show that the force is 6.6. So remember, I said here was my resultant. It was made of a component 2.17 newtons west from the 2.5 Newton force. It was composed of a 6.25 north force. And now I should be able to show that R is 6.6 using Pythagoras Theorem. So step 5 up there on the chalkboard says use Pythagoras Theorem now. Now that you've added up all the x's and y's, you've got a new right triangle to work with. And so it's true that R squared equals 6.25 squared plus 2.17 squared. So R should equal the square root of the sum of those squares. Now, rather than typing in 2.17, I've got the 2.16, the thing I rounded, that's still in my calculator, so I'll just keep it there, right? Square that, plus 6.25 squared equals, so that's the sum of the squares. Taking the square root now, I get R equal to 6.6143, which is indeed about 6.6 newtons, and it all checks out. I've shown that the force is that. Note that I can't just write something down like 5.6 plus 1 equals 6.6. Check, got it, right? It has to be the correct working. It can't just be any working that leads to this answer. There's lots of math problems that equal 6.6, but only this one is the one that shows that the resultant force is 6.6. Remember the nice thing about net forces and acceleration, the universe that we live in, it's pretty, common sense works for, big objects, a few kilograms moving a few meters per second. Your common sense doesn't work if we're doing like quantum mechanics, submicroscopic stuff, or relativity close to the speed of light. Common sense doesn't help anymore. But for this, it's like, okay, if I push something, it accelerates in that direction. This thing wants to know the angle between the direction of the acceleration. Well, that's the same as my resultant force, the one that went that way. And the direction of the 7.5 Newton force, which is, remember, my north force. So it wants this angle right here. Remember, I know that there's a 2.17 Newton vector that way and a 6.25 Newton vector this way. That's how I solved for my resultant, or I showed that my resultant was 6.6. For me, the easiest way to calculate this angle, the angle they want to know, right, between my acceleration, which is my net force, right? That's the idea here, that these acceleration and net force vectors point in the same way. This thing will accelerate in the direction of the net force. They want to know the angle between that and here. But it's easy for me to calculate this angle here. I'll call it alpha. And if I know the angle alpha, I could just say 90 minus alpha gives me theta, right? Like I have a 90-degree angle between them, like this plus this is 90. So it's easy to calculate alpha with an inverse trig function. The inverse tangent of the opposite over the adjacent solves for the angle. Before we had always used, and I know this is going to like blurry the camera. Oh, it didn't. Before it was always the function of the angle. The function of the angle equals the ratio of sides, and we're solving for an unknown side. Here we know all the sides, right? Now we're solving for the angle. So we have to use the inverse function. I failed half a semester of college trig not knowing that. One day I went up to my professor and I said, I can't get these questions right. Like, I don't know how to solve for the angle. I can work with the triangles. And he's like, oh, just hit that second key in your calculator. Just you take the inverse. I'm like, oh, I failed half a semester of college trig, and it was literally a button I needed to push. I missed that day, or was absent-minded when he explained it. It took a question I needed to ask to say, how do I solve for the angle? Right? And as soon as he showed it to me, it's like so simple. Okay, hit this button. So my calculator, I got my 6.25 divided by my 2.17. That's opposite over adjacent. That's the ratio of sides. There's the tangent, but if you look above it, I got the tangent to the -1. So shift, that's all I needed to know. Like, oh, okay, one button away from the correct answer. It's like, So alpha is 70.85. So then what's theta up here? It's 90 minus that, right? Because I got a 90-degree angle between them. So the easy way for me to calculate 90 minus this is to just make that negative in my calculator and then add 90 to it. So I get 19.1 or just 19 degrees. Oh, they already had the degree right there. Okay. So the angle that they're asking for is 19 degrees. That's the angle between the 7.5 Newton force and the resultant acceleration, the resultant force. Okay, 19 degrees. And this has been another work example with Dr. Schleif. We'll see you next time.